Across the planet, separated by thousands of kilometers and thousands of years, ancient peoples built monuments of staggering scale and precision. Stones weighing hundreds of tons were moved and positioned with accuracy that rivals modern engineering. Structures aligned with celestial events with mathematical precision. Civilizations invested enormous resources in projects that served no practical survival purpose. Yet these monuments persist, standing as silent testimony to human ingenuity, ambition, and meaning-making. The question that draws us into this exploration is both simple and profound. How did they do it? And what does it reveal about human capability? Over the next 2.5 hours, we'll journey across continents and centuries, examining some of humanity's most remarkable achievements. From Stonehenge's astronomical precision on the English plains to Göbekli Tepe's temples in ancient Turkey, from Baalbek's impossible foundation, stones in Lebanon, to Puma Punku's interlocking blocks in the Andes, from Easter Island's Moai to the pyramids of Egypt, we'll explore what researchers have discovered about these structures and what mysteries still perplex us. This exploration is built on decades of archaeological research, astronomical analysis, and experimental archaeology. We'll examine what we know with confidence, explore what scholars still debate, and acknowledge, honestly, what remains unknown. But this is also a human story. It's about the people who built these monuments, their knowledge, their motivations, their understanding of the world. It's about how ancient civilizations organized labor, preserved knowledge across generations, and invested resources in projects that express their deepest values and beliefs. It's about what these ancient achievements can teach us about human nature, about sustainability, about meaning-making, and about the limits of our own understanding. We'll take our time with this exploration, moving thoughtfully through evidence and ideas. There's no rush. We'll examine construction techniques, consider astronomical alignments, explore labor systems, and contemplate mysteries that have resisted definitive answers for centuries. This is a journey designed for careful consideration, perfect for falling asleep while remaining genuinely interesting for drifting off while learning something real about our ancient past. So settle in, get comfortable, and let's begin this journey together. Stones that shouldn't exist. Across the planet, separated by thousands of kilometers and centuries of time, ancient peoples built monuments that seem to defy the capabilities we typically assign to their eras. These aren't scattered anomalies, but part of a consistent pattern, a global impulse to move, shape, and position stones of extraordinary weight with precision that rivals modern engineering. The question that draws us into this exploration is both simple and profound. How did they do it? In Wiltshire, England, on the Salisbury Plain, sarsen stones weighing 25 tons stand arranged in perfect circles, their surfaces weathered by 4,500 years of exposure to wind and rain. In Peru's high Andes, at elevations where oxygen grows thin and the air bites cold, granite blocks fit together so precisely that a knife blade cannot slip between them. In Turkey's limestone plateau, T-shaped pillars rise from bedrock with astronomical alignments so exact that they mark celestial events with calendar-like accuracy. In Lebanon's Bekaa Valley Foundation, stones exceed 800 tons, some of the heaviest ever quarried by human hands. On Easter Island, a remote speck of land in the Pacific Ocean, 887 statues dot the landscape, each carved from volcanic stone and weighing up to 82 tons. The conventional narrative tells us these were built with copper tools, wooden sledges, and human muscle. The story is neat, comprehensible, and largely true. Yet questions persist beneath this comfortable explanation. Questions that have occupied archaeologists, engineers, and historians for generations. How did Easter Islanders transport 10-ton statues across treeless terrain, moving them kilometers from quarries to coastal platforms? How did Baalbek's builders quarry stones so massive that modern equipment, cranes, hydraulic systems, diesel engines struggles to move them? Why do these structures built by unconnected civilizations, separated by vast distances and centuries, align with celestial events, solstices, equinoxes, star positions with such consistent precision that coincidence seems implausible? Archaeologists and engineers have proposed theories to address these questions. Ramp systems carefully calculated and constructed from earth and stone could have allowed workers to move massive blocks incrementally upward. Water lubrication techniques using water to reduce friction between stone and sledge could have made movement more efficient. Lever systems employing principles of mechanical advantage could have lifted and positioned stones with less force than direct pulling. Organized labor forces, coordinated through systems we're only beginning to understand, could have mobilized thousands of workers towards sustained effort across years or decades. Some theories hold water. They're supported by experimental archaeology, mathematical modeling, and archaeological evidence. Others strain credibility, requiring assumptions about lost technology or capabilities that stretch our understanding of what was possible with available resources. What remains certain, however, is that these builders possessed sophisticated knowledge of mathematics, astronomy, and engineering that challenges our assumptions about primitive societies. They understood geometry well enough to create structures of stunning precision. They possessed astronomical knowledge, allowing them to track celestial cycles and predict celestial events years in advance. They could organize labor, manage resources, and sustain effort across generations. Consider the precision we're discussing. At Stonehenge, the stones align with the summer solstice sunrise and winter solstice sunset. The heel stone marks the midsummer sunrise with such accuracy that the alignment remains valid after 4,500 years of Earth's precession. This wasn't approximation. It was deliberate calculation, based on careful observation. At Baalbek Foundation, stones fit together with millimeter accuracy, requiring no mortar or binding agents. The stones have remained stable through earthquakes that destroyed surrounding structures. This precision suggests not experimentation, but confident execution, implying builders had experience with similar projects or inherited knowledge from earlier traditions. The scale of these projects magnifies the mystery. The Great Pyramid of Giza contains 2.3 million stone blocks, averaging 2.5 tons each. Some weigh significantly more. The entire structure rises 146 meters into the Egyptian sky, and its base covers 5.3 hectares. Construction required moving approximately 5.75 million tons of stone. Stonehenge's bluestones were transported from Wales, a distance of 240 kilometers across terrain and water, without wheeled vehicles or draft animals. Easter Island's moai were moved across the island, some traveling 10 kilometers from quarries to coastal platforms. These weren't small projects executed by small teams. They required sustained effort, sophisticated planning, and social organization of considerable complexity. What draws us to these monuments is not merely their scale, but their precision, combined with their apparent impossibility. A large stone can be moved through brute force and sufficient labor, but moving a stone with precision, positioning it exactly where it needs to be, maintaining astronomical alignment, and fitting it perfectly with neighboring stones, this requires knowledge and capability that seems to exceed what we expect from ancient societies. Yet the monuments stand as evidence that this capability existed. These structures represent more than construction projects. They reveal sophisticated minds solving complex problems with available resources. They demonstrate that human ingenuity, mathematical understanding, and organizational capability can accomplish extraordinary things without modern machinery. Yet gaps remain in our understanding of their methods and motivations. We possess fragments of knowledge. Experimental archaeology provides insights into possible techniques. Archaeological evidence reveals organizational structures. Astronomical analysis confirms intentional alignments, but the complete picture remains partially obscured. The monuments themselves persist, outlasting the civilizations that built them, inviting us to understand not just how they were built, but why ancient peoples invested such extraordinary effort in their construction. As we move forward in this exploration, we'll examine specific monuments in detail, investigating what we know about their construction, what remains mysterious, and what these ancient achievements reveal about human capability and the knowledge systems that guided ancient civilizations. We'll begin with Stonehenge, perhaps the most iconic of these monuments, and explore how Neolithic peoples created an astronomical observatory of stunning precision on the Salisbury Plain. Stonehenge, the celestial calculator. We've seen how ancient peoples across the globe possess the capability to move and position stones of extraordinary weight. Now let's turn to one of the most iconic monuments of prehistory, a structure that reveals not just engineering prowess, but sophisticated astronomical knowledge. On the Salisbury Plain in Wiltshire, England, a circle of stones has stood for over 4,000 years, marking celestial events with precision that continues to astound modern observers. Stonehenge represents one of prehistory's most enigmatic structures, yet its construction timeline reveals something equally fascinating: patience. Around 3100 BCE, construction began on the site. This wasn't a project completed in a generation or even several generations. Over approximately 1,500 years, multiple phases of construction transformed the landscape. The outer sarsen circle contains 30 upright stones, each weighing approximately 25 tons, topped with 7-ton lintels that form a continuous ring. The inner horseshoe of trilithons, pairs of stones topped with lintels, reaches heights of 24 meters, with the largest stones weighing up to 50 tons. Within these structures, bluestones transported from the Preseli Mountains in Wales, 240 kilometers away, form additional circles and arrangements. The precision of Stonehenge's construction becomes apparent when we examine its astronomical alignments. The stones align with the summer solstice sunrise and winter solstice sunset. The heel stone, positioned outside the main circle, marks the midsummer sunrise with such accuracy that the alignment remains valid after 4,500 years of precession, the gradual shift in Earth's rotational axis. The station stones, 4 smaller stones forming a rectangle within the monument, aligned to lunar extremes. These weren't accidents or approximations. The consistency and precision of these alignments indicate deliberate astronomical engineering, suggesting builders possessed a knowledge of celestial mechanics and the ability to translate that knowledge into stone. How did Neolithic peoples acquire such astronomical knowledge? The answer lies in patient observation. Tracking celestial cycles requires watching the sky systematically across years and decades. The summer and winter solstices represent the extreme positions of the sun's rising point on the horizon. Observing these extremes across multiple years allows prediction of their recurrence. The lunar cycle presents greater complexity. The moon's rising point shifts gradually across an 18.6-year cycle. Understanding this cycle required observations spanning decades, suggesting communities committed to sustained astronomical study. Consider the practical implications of this knowledge. For agricultural societies, understanding seasonal cycles was essential. Planting and harvest times depended on seasonal changes marked by celestial events. A structure that accurately marked solstices could serve as a calendar visible to entire communities. This dual function, spiritual significance, combined with practical utility, likely explains why such effort was invested in Stonehenge's construction. The transportation of blue stones from Wales presents a particularly intriguing challenge. These stones, weighing approximately 4 tons each, were quarried in Wales and somehow moved 240 kilometers to the Salisbury Plain. Recent experimental archaeology has provided insights into how this might have been accomplished. Teams of approximately 150 people could move a 4-ton stone using wooden sledges and water lubrication techniques. The route likely involved water transport stones loaded onto wooden rafts, floated down Welsh rivers, across the Bristol Channel, and up English rivers, then transported overland to the site. Experimental trials have confirmed this route's feasibility, though the logistical coordination required remains staggering. How did they know? How did they measure? How did they coordinate such efforts across vast distances? These questions lead us to perhaps the most intriguing aspect of Stonehenge, the evidence of social organization and knowledge systems that made such projects possible. Excavations at the site have revealed cremated remains of hundreds of individuals, suggesting Stonehenge functioned as a burial ground of considerable significance. Isotope analysis of skeletal remains has revealed something remarkable. Visitors traveled from across Britain and continental Europe. Strontium isotope ratios in tooth enamel indicate individuals from distant regions, suggesting Stonehenge attracted people from far and wide. The site clearly served multiple functions simultaneously. It was a burial ground, a ceremonial center, and an astronomical calendar. Archaeological evidence suggests ritual feasting occurred at the site with animal bones, indicating consumption of cattle and other animals. The arrangement of stones suggests processional routes and viewing areas, implying organized ceremonies attended by multiple individuals. The precision of astronomical alignment suggests formal astronomical knowledge, possibly taught to specialists who maintained and interpreted the monument. The construction itself reveals organizational sophistication. Building Stonehenge required quarrying stones, transporting them across vast distances, shaping them with precision, and positioning them exactly. This demanded coordination of labor management of resources and sustained commitment across generations. Workers needed to be fed, housed, and motivated. Materials needed to be sourced and transported. Knowledge needed to be preserved and transmitted across generations to maintain consistency in construction. These requirements suggest social structures capable of organizing large-scale projects, capabilities we're only beginning to appreciate in Neolithic societies. The why of Stonehenge remains debated among scholars. Was it primarily a temple, a sacred space for ritual and spiritual practice? Was it a healing center, as some theories propose, with people traveling to the site seeking cure from ailments? Was it an astronomical school where specialists studied celestial mechanics? The evidence suggests all these functions coexisted, serving a culture with sophisticated understanding of celestial mechanics and the spiritual significance of cosmic order. The investment of such enormous resources over such an extended period suggests Stonehenge held profound meaning for the communities that built it. Stonehenge reveals that astronomical knowledge wasn't the province of later civilizations alone. It flourished in prehistoric Britain, suggesting a lost intellectual tradition, a sophisticated understanding of the cosmos that guided the construction of monuments and the organization of society. The precision of Stonehenge's alignments demonstrates that Neolithic peoples possessed the observational skills and mathematical knowledge to track celestial cycles and predict celestial events. This challenges our assumptions about the intellectual capabilities of prehistoric societies and suggests that knowledge systems of considerable sophistication existed long before written history. From this understanding of Stonehenge's astronomical sophistication, we can now turn to another remarkable site, one that predates Stonehenge by thousands of years and raises even more profound questions about the origins of monumental architecture and astronomical knowledge. Göbekli Tepe, the world's first temple. The astronomical knowledge we discovered at Stonehenge emerged from a society that had already developed agriculture, permanent settlements, and complex social hierarchies. But what if we could trace monumental architecture and spiritual ambition even further back in time to a period before farming, before cities, before the assumed prerequisites for civilization itself? In 1994, archaeologist Klaus Schmidt excavated a hilltop in southeastern Turkey and found something that would fundamentally challenge our understanding of human development. Göbekli Tepe, which translates to Potbelly Hill, sits on a limestone plateau in the Şanlıurfa region of Turkey, near the Syrian border. What Schmidt and his team uncovered there has rewritten prehistory. The site contained T-shaped limestone pillars, some reaching 7 meters high, carved with intricate images of scorpions, snakes, and foxes. Radiocarbon dating placed the construction of these structures at approximately 9600 BCE. This date is startling in its implications. Göbekli Tepe predates agriculture by roughly 4,000 years. It predates permanent settlements. It predates the assumed prerequisites for monumental architecture, organized labor forces, centralized authority agricultural surplus to support non-productive workers. This challenged everything archaeologists thought they understood about human development. The conventional narrative suggested that agriculture enabled civilization. Farming allowed populations to settle in one place, accumulate surplus, develop social hierarchies, and invest resources in monumental projects. Yet here stood a structure requiring sophisticated planning, organized labor, and shared purpose among hunter-gatherer communities. The very existence of Göbekli Tepe suggested that spiritual and intellectual ambition could drive human cooperation long before practical survival needs demanded it. The site contains at least 20 stone towers or enclosures arranged in circles. Each T-shaped pillar weighs up to 15 tons and was quarried from bedrock using stone tools, no metal implements, no modern machinery. The precision of placement and carvings suggests advanced understanding of geometry and engineering. The pillars feature carved reliefs depicting animals with remarkable detail. The T-shape itself remains enigmatic. Some researchers suggest the pillars represent anthropomorphic figures, stylized human forms, with a horizontal bar representing arms. Others propose astronomical functions with the T-shape oriented toward celestial events. The true meaning remains unclear, inviting ongoing interpretation. What makes Göbekli Tepe's discovery even more intriguing is what hasn't been excavated. Archaeological surveys indicate that only approximately 5% of the site has been excavated. Beneath the surface lie structures and artifacts yet to be discovered. What lies beneath remains unknown, but the scale of unexcavated material suggests the site may be far larger and more complex than current understanding indicates. This unknown territory represents both mystery and promise. Future excavations may reveal additional insights into the site's function and significance. The evidence of human activity at Göbekli Tepe tells the story of ritual and community gathering. Bone tools and flint blades have been recovered, indicating tool-making activities. Animal remains, particularly bones of wild boar and gazelle, suggest ritual feasting. The quantity and distribution of animal bones indicate that substantial numbers of people gathered at the site for communal meals. These weren't small family-scale gatherings, but large assemblies involving dozens or possibly hundreds of individuals. The logistics of feeding such gatherings, obtaining and preparing food, and organizing the gathering itself required coordination and planning. How did they know? How did they measure? How did they coordinate such efforts across vast distances? These questions lead us to perhaps the most intriguing aspect of Göbekli Tepe, the evidence of knowledge systems and social organization that made such projects possible. The precision of the pillars' placement and carving suggests formal training in stoneworking. The consistency of design across multiple enclosures suggests shared architectural principles and possibly shared religious or spiritual concepts. The scale of the project suggests individuals with authority capable of organizing labor and directing construction. The carvings at Göbekli Tepe depict predators and dangerous animals, scorpions, snakes, foxes, boars, rather than prey species like deer or gazelle. This is significant. If the site served primarily practical purposes like food storage or hunting coordination, we would expect depictions of prey animals. Instead, the artistic focus on predators and dangerous creatures suggests symbolic or spiritual rather than practical purpose. These animals may have held spiritual significance represented in stone as part of religious practice or cosmological belief systems. Klaus Schmidt, who led excavations at Göbekli Tepe for decades until his death in 2014, proposed a revolutionary theory. He suggested that Göbekli Tepe represented humanity's first monumental religious center, built by nomadic peoples who gathered seasonally for ritual purposes. This implies that religious motivation preceded agricultural settlement, a reversal of conventional understanding. Rather than agriculture enabling religion and monumental architecture, Schmidt's theory suggests that spiritual and intellectual ambition drove the development of social structures capable of organizing large-scale projects. The desire to create sacred spaces and engage in ritual may have been a primary driver of human cooperation and social development. This perspective shifts how we understand human motivation and development. It suggests that spiritual and intellectual pursuits aren't luxuries that emerge only after practical survival needs are met. Instead, they may be fundamental to human nature, driving cooperation and social organization from the earliest periods of complex human society. The investment of enormous resources in creating Göbekli Tepe quarrying stones, transporting them, carving them with precision, organizing gatherings, suggests that these activities held profound meaning for the communities involved. Göbekli Tepe suggests that spiritual and intellectual ambition drove human cooperation long before practical survival needs demanded it, fundamentally altering our conception of human development. The site demonstrates that monumental architecture, organized labor, and shared religious purpose emerged not as consequences of agricultural settlement, but as expressions of human nature that may have preceded agriculture itself. The precision of construction and the evidence of ritual gathering suggest minds engaged in systematic thinking about the cosmos and humanity's place within it. As we continue investigating Göbekli Tepe and sites like it, we're discovering that the origins of civilization may be far more complex and spiritually motivated than previously understood. From these ancient Turkish hills, we now turn our attention to another remarkable site, one that presents different mysteries, but equally profound questions about ancient engineering and astronomical knowledge. Baalbek, the impossible foundation. We've explored how ancient peoples in different regions developed sophisticated astronomical and architectural knowledge. Now we turn to a site that presents a different kind of mystery, one involving stones so massive that their very existence challenges our understanding of ancient engineering capabilities. In Lebanon's Bekaa Valley, in a region that has witnessed countless civilizations rise and fall, stands a structure that continues to perplex archaeologists and engineers alike. The Temple of Jupiter at Baalbek was constructed by Roman engineers around 60 CE during the reign of Emperor Nero. It stands as one of the largest temples ever built in the Roman Empire, a testament to Roman architectural ambition and engineering prowess. Yet beneath this Roman temple lies something older and more mysterious, a foundation, containing stones so massive that they seem to exceed the capabilities of any known ancient civilization. This foundation, called the trilithon, consists of 3 limestone blocks, each weighing approximately 800 tons. The largest, known as the Stone of the South, measures 21.5 meters long, 4.8 meters high, and 4.2 meters deep. To place these measurements in perspective, this single stone weighs roughly equivalent to 600 modern automobiles, yet it was moved and positioned with precision that rivals modern construction standards. These are not the heaviest stones ever moved at Baalbek. The western platform of the temple complex contains blocks exceeding 900 tons, yet the precision of the trilithon's placement defies easy explanation. The 3 massive stones fit together with millimeter accuracy, their surfaces aligned so precisely that no mortar was required. They have remained stable through earthquakes that destroyed surrounding structures, suggesting engineering knowledge of seismic stability or extraordinary luck in their positioning. The durability of this foundation, standing for nearly 2,000 years without significant degradation or displacement, suggests that whoever built it understood not just how to move massive stones, but how to position them for long-term stability. The question of who built this foundation becomes more intriguing when we consider the historical record. Roman engineers built the temple above this foundation, but did they build the foundation itself? The evidence suggests otherwise. The Roman construction style differs markedly from the trilithon's design and execution. Phoenician, Persian, and Hellenistic periods all left marks on the site through various modifications and additions, yet none of these civilizations claimed responsibility for the trilithon in historical records or inscriptions. Local tradition, preserved in folklore and oral history, attributes the massive stones to giants or supernatural beings, a common pattern. When ancient peoples encountered monuments they couldn't explain through their own knowledge, modern archaeological analysis reveals that the stones were quarried locally. Nearby stone pits show evidence of extraction that began but was abandoned, suggesting that quarrying operations were discontinued before completion. This raises intriguing questions. Why were these massive stones quarried? What was the original plan? Did the project change, or was it abandoned due to practical difficulties? The answers remain unclear, but the evidence of local quarrying indicates that builders didn't transport these stones from distant locations. They moved them across relatively short distances, approximately 900 meters from quarry to final position. This proximity might seem to simplify the problem, yet it actually magnifies the mystery. Moving a 900-ton stone across 900 meters of terrain without modern machinery presents extraordinary challenges. Proposed methods include wooden sledges, ramps constructed from earth and stone, and lever systems employing principles of mechanical advantage. Theoretically, these methods could work. Experimental archaeology has demonstrated that teams of sufficient size using water lubrication to reduce friction could move multi-ton stones across level terrain. But scaling these methods to 900-ton blocks requires assumptions about labor organization and engineering knowledge that strain credibility. Consider what such a project would require. Moving a 900-ton stone would demand hundreds, possibly thousands of workers, coordinated through systems of communication and organization. Ramps would need to be constructed and maintained. Sledges would need to be built from timber. Water sources would need to be available for lubrication. Food and shelter would need to be provided for the workforce. The logistics alone suggest a society with substantial resources and organizational capability. Yet the historical record provides no clear documentation of such a project or the civilization that undertook it. The precision of the trilithon's placement suggests not experimentation, but confident execution. The stones are positioned exactly where they need to be, fitted together with such accuracy that adjustments would have been minimal. This implies builders had experience with similar projects we haven't yet identified. Were there other massive stone structures built by the same civilization? Have they been destroyed or remain undiscovered? The evidence suggests a tradition of monumental stone construction, yet we possess limited archaeological evidence of other examples. Why build such massive foundations? Several theories have been proposed. Religious significance may have motivated the construction. Massive foundations could have served symbolic purposes representing divine power or cosmic order. Practical stability on seismic terrain offers another explanation. The Bekaa Valley experiences earthquakes, and massive, precisely fitted stones might provide superior stability compared to smaller blocks. The weight and precision of the trilithon could distribute seismic forces more effectively than conventional construction methods. This practical explanation has merit, yet it doesn't fully account for the extraordinary effort invested in creating such massive stones when smaller blocks would have served the same structural purpose. The most intriguing aspect of Baalbek's foundation is what it suggests about technological continuity and knowledge loss. The precision and scale of construction implies sophisticated engineering knowledge, yet this knowledge appears to have been lost or abandoned. The Romans who built the temple above this foundation did not replicate the trilithon's construction method. Later civilizations that occupied the site made modifications, but did not attempt similar massive stone construction. This suggests that the knowledge required to quarry, transport, and position such massive stones was not transmitted to subsequent generations, or was deliberately abandoned in favor of different construction methods. Baalbek's foundation stones represent either extraordinary Roman engineering or inherited knowledge from earlier civilizations, raising profound questions about technological continuity and knowledge loss across centuries. The precision and scale of construction challenge our assumptions about what was possible with ancient technology. The absence of clear historical documentation about the trilithon's construction suggests either that records have been lost or that the structure predates the civilizations whose records we possess. As we continue investigating Baalbek and similar sites, we're discovering that ancient engineering capabilities may have been more sophisticated than historical records indicate, and that knowledge systems of considerable complexity may have flourished and then disappeared, leaving only their monumental remains as evidence of their existence. From these Lebanese hills, we now turn to another remarkable site in the Andes, where different challenges and different solutions reveal yet another facet of ancient engineering achievement. Puma Punku, the ANDEAN puzzle. We've examined massive stones positioned with precision in Lebanon's valley. Now we travel to a different continent, to a different altitude to discover similar engineering challenges solved through methods that remain partially mysterious. High in the Andes Mountains on the Bolivian Altiplano at 3,150 meters above sea level lie the ruins of Puma Punku, a site that reveals sophisticated engineering flourishing independently in one of Earth's most challenging environments. The name Puma Punku translates to Puma's Gate in the Aymara language, referring to a legendary feline deity in Andean cosmology. The site contains stone blocks of extraordinary precision, some weighing 130 tons, fitted together so precisely that a knife blade cannot slip between them. The blocks feature complex geometric shapes, L-shaped, T-shaped, and interlocking forms that required sophisticated planning and execution. Unlike the massive monoliths of Baalbek or Stonehenge, Puma Punku's stones were designed to interlock with one another, creating a three-dimensional puzzle of stone that has remained stable for over 1,000 years, despite earthquakes, weathering, and human disturbance. Construction likely occurred between 500 and 1000 CE during the height of the Tiwanaku civilization. The Tiwanaku culture flourished in the Andes for approximately 500 years, developing sophisticated systems of agriculture, astronomy, and architecture. Puma Punku served as a ceremonial and administrative center, though its exact function remains debated among scholars. Some researchers propose it functioned as a temple or sacred space. Others suggest it served administrative purposes, coordinating the complex systems required to manage Tiwanaku civilization across varied altitudes and climates. The most likely explanation is that it served multiple functions simultaneously, a pattern we've observed at other ancient sites. The Gateway of the Sun, a monolithic arch carved from a single stone block, stands as perhaps Puma Punku's most iconic feature. This gateway displays astronomical alignments and intricate geometric patterns carved into its surface. The gateway's design suggests sophisticated understanding of astronomy and geometry. The patterns carved into the gateway depict human and animal figures arranged in geometric relationships, suggesting cosmological significance. The gateway's orientation aligns with celestial events, indicating that Tiwanaku builders, like their counterparts in other regions, invested effort in connecting earthly structures to cosmic order. The precision of Puma Punku's stone fittings suggests advanced understanding of geometry and engineering principles. Each block was individually shaped to fit its neighbors perfectly. This required measurements, calculations, and quality control throughout the construction process. The builders used stone tools. No metal implements have been found at the site, yet achieved results comparable to modern masonry. The interlocking design means that each stone depends on its neighbors for stability. A single poorly fitted stone could compromise the entire structure. This suggests rigorous quality control and skilled craftspeople capable of executing complex designs with minimal error. How were such massive blocks transported to high altitude? The nearest quarries lie several kilometers away across terrain that rises and falls significantly. Moving a 130-ton block up steep mountain slopes without wheeled vehicles or draft animals presents extraordinary challenges. Proposed methods include wooden sledges, water lubrication techniques to reduce friction, and organized labor teams of substantial size. Experimental archaeology has provided insights into feasibility, yet the logistics remain staggering. Moving a 130-ton stone up mountainous terrain would require hundreds of workers coordinated through systems we can only partially reconstruct. The high altitude itself presents additional challenges. At 3,050 meters above sea level, oxygen levels are approximately 60% of sea level concentrations. Workers would experience the altitude sickness, reduced physical capability, and increased fatigue. Yet the Tiwanaku civilization developed sophisticated systems for managing high-altitude environments. Archaeological evidence suggests they used terraced agriculture, irrigation systems, and storage facilities to manage resources across different altitudes. This organizational capability, developed for agricultural purposes, could have been applied to construction projects. Consider the practical implications of construction at high altitude. Quarrying stone requires sustained physical effort in an environment where oxygen is limited. Transporting stones requires coordination of large labor forces in challenging terrain. Shaping and fitting stones requires skilled craftspeople working in cold, thin air. Food and shelter must be provided for workers. The entire project requires social organization and resource management of considerable sophistication. Yet the Tiwanaku civilization possessed these capabilities, having developed complex systems for managing their challenging environment. The site shows evidence of later Inca modification and incorporation. The Inca civilization, which rose to prominence after the Tiwanaku civilization's decline, recognized Puma Punku's significance and incorporated it into their own architectural and religious traditions. The Inca made modifications to the site, adding structures and adapting existing ones to fit their own aesthetic and functional requirements. This suggests knowledge, transfer, and respect for earlier engineering achievements. The Inca, renowned for their own sophisticated architecture, recognized the engineering sophistication of their predecessors and chose to preserve and adapt rather than replace. The relationship between Tiwanaku and Inca civilizations suggests continuity of knowledge across centuries. The Inca adopted and adapted Tiwanaku architectural principles, suggesting that knowledge of construction techniques, geometric principles, and engineering methods was transmitted between civilizations. This transmission may have occurred through direct contact through conquest and incorporation of Tiwanaku territories into Inca domains or through cultural memory and oral tradition. The evidence suggests that sophisticated engineering knowledge persisted across generations and civilizations rather than being lost and rediscovered. The astronomical alignments at Puma Punku demonstrate that Andean builders, like their counterparts in other regions, possessed sophisticated astronomical knowledge. The gateway of the sun's orientation marks celestial events with precision. This suggests systematic observation of celestial cycles and mathematical knowledge to translate observations into architectural design. The consistency of astronomical alignment across different cultures and continents raises intriguing questions about knowledge transmission or independent discovery of similar astronomical principles. Puma Punku demonstrates that sophisticated engineering flourished independently in the Andes, raising questions about whether such knowledge developed locally or was transmitted through now-lost networks of contact. The precision of construction, the complexity of design, and the scale of effort invested suggest engineering traditions of considerable sophistication. Yet we possess limited evidence of earlier sites demonstrating the development of these capabilities. This raises the possibility that either earlier sites remain undiscovered, or that knowledge was transmitted from sources we haven't yet identified. The Tiwanaku civilization appears fully formed in the archaeological record with sophisticated capabilities already developed. This pattern, civilizations appearing with advanced capabilities without clear evidence of developmental stages, appears repeatedly in the archaeological record, suggesting either gaps in our knowledge or transmission of knowledge across now-lost networks. From these high Andean plateaus, we turn to an even more isolated location, a remote Pacific island where engineering challenges were solved through different methods and different materials. Easter Island engineering at the edge of the world. We've explored how ancient civilizations in mountains and valleys solved extraordinary engineering challenges. Now we journey to one of Earth's most isolated locations, a remote Pacific island, where an ancient population created hundreds of monumental statues without access to the resources that enabled construction elsewhere. Easter Island, situated 3,500 kilometers from the nearest inhabited land, presents perhaps the most puzzling monument-building achievement of all. Easter Island contains 887 Moai stone statues that have captured human imagination for centuries. These figures average 4 meters in height and weigh approximately 5 tons, though some reach 10 meters tall and weigh up to 82 tons. The statues depict human figures with distinctive elongated faces, prominent noses, and forward-gazing eyes. Most feature white coral eyes that were inserted after the statues were erected, giving them an unsettling, almost watchful quality. Construction spanned roughly 1000 to 1600 CE, a period of approximately 600 years, during which the island's population devoted extraordinary resources to carving and transporting these figures. The statues were quarried from Ranararaku, a volcanic crater on the island's eastern side. The crater contains tough stone, compressed volcanic ash, ideal for carving with stone tools. Incomplete statues remain in the quarry, providing invaluable insight into construction techniques. Some statues lie partially carved, abandoned mid-project. Others show evidence of tool marks revealing the methods carvers employed. The carvers used basalt-picked stones harder than the tuff to shape the figures. The precision of facial features and body proportions suggests artistic training and established aesthetic standards. The consistency of design across hundreds of statues indicates a shared artistic tradition maintained across generations. The scale of the quarrying operation was substantial. Researchers estimate that carving a single moai required weeks or months of sustained effort. Multiple carvers would work simultaneously on different statues, suggesting organized labor systems and resource management. Food and water would need to be provided for workers. Tools would need to be maintained and replaced. The logistics of maintaining a quarrying operation of this scale required social organization and planning. Yet the Rapa Nui people, as the island's inhabitants are known, possess these capabilities, having developed sophisticated systems for managing their island's limited resources. Transportation presented extraordinary challenges that distinguish Easter Island from other monument-building sites. The island lacks trees suitable for sledges or rollers. In fact, by the time statue production was well underway, the island had become nearly treeless. Yet statues were moved across the island, some traveling 10 kilometers or more from quarries to coastal platforms called ahu. Oral traditions preserved by island inhabitants describe statues walking to their destinations, a metaphor that may preserve memory of actual transportation methods. The image of statues walking suggests a specific technique, possibly involving rocking motions that allowed statues to move forward incrementally. Recent experimental archaeology has provided insights into feasibility. Researchers conducted experiments moving replica moai using techniques reconstructed from archaeological evidence and oral tradition. Teams of 25 to 30 people could move a 5-ton statue using wooden sledges and rope with water applied to reduce friction between stone and sledge. The experiments demonstrated that the method was viable, though labor-intensive. Scaling this method to 82-ton statues would require proportionally larger teams, possibly 500 or more people, and extended effort. The logistics suggest organized labor, sophisticated resource management, and sustained commitment across generations. The question of where wood came from becomes particularly intriguing. Easter Island's current landscape is nearly treeless, dominated by grass and low vegetation. Yet the island once supported substantial forests. Pollen analysis reveals that the island was covered with palm trees and other species suitable for providing wood for construction. As statue production intensified, demand for wood increased. Wood was needed for sledges, rollers, and tools. Wood was needed for fuel to cook food for workers. The environmental cost of statue production became increasingly severe. Deforestation likely resulted directly from construction demands. Each statue required resources extracted from the island's limited ecosystem. By approximately 1600 CE, the island was nearly treeless. Statue production ceased abruptly around this time. Oral traditions describe warfare and societal collapse coinciding with environmental exhaustion. Archaeological evidence supports this narrative. Settlement patterns change around 1600 CE, suggesting social disruption. Evidence of conflict appears in the archaeological record. The population, which may have reached 10,000 or more at its peak, declined substantially. The collapse of Easter Island civilization appears linked directly to environmental degradation caused by unsustainable resource use. This environmental collapse presents a cautionary narrative about the consequences of overexploiting limited resources. The Rapa Nui people invested enormous effort in creating monuments that express their spiritual beliefs and social identity. Yet in doing so, they depleted the resources necessary for their civilization's survival. The statues that represented their culture's greatest achievement ultimately contributed to its decline. This pattern, civilizations consuming resources unsustainably and facing collapse, appears repeatedly in human history, from Easter Island to the Maya civilization to modern industrial societies. The moai themselves reveal something profound about human nature and motivation. Despite living on a remote island with limited resources, the Rapa Nui people invested centuries in creating hundreds of monumental statues. This investment wasn't driven by practical necessity. The statues didn't provide food, shelter, or protection. Instead, they expressed spiritual beliefs, honored ancestors, and demonstrated social status and power. This suggests that spiritual and cultural motivations can drive human behavior as powerfully as practical survival needs. The Rapa Nui people chose to invest their resources in monuments rather than in sustainable resource management, a choice that ultimately proved catastrophic. Easter Island's moai represent both human ingenuity and the consequences of unsustainable resource use, suggesting ancient societies grappled with ecological limits, much like modern civilization. The statues demonstrate remarkable engineering and artistic achievement, yet they also demonstrate how civilizations can become trapped in patterns of behavior that ultimately prove self-destructive. The Rapa Nui people possess the knowledge and capability to manage their island's resources sustainably. Yet cultural and spiritual commitments to monument building overrode practical considerations. Understanding Easter Island's history offers perspective on contemporary challenges, the tension between cultural values and environmental sustainability, between short-term desires and long-term consequences, between individual and collective benefit. From this remote Pacific island, that we now turn to examining the astronomical alignments that connect many of these ancient monuments, exploring what celestial knowledge guided their construction. Astronomical alignments, coincidence or calculation. We've examined individual monuments across the globe, each remarkable in its own way. Now we step back to observe a pattern that connects them, a consistency so striking that it challenges our understanding of ancient knowledge and possibly suggests contact between distant civilizations. When we examine these structures together, a celestial theme emerges with unmistakable clarity. The pattern is undeniable and spans continents and centuries. Stonehenge aligns with solstices and lunar extremes, its stones positioned to mark the sun's rising and setting at the year's turning points. The Giza pyramids align with cardinal directions, north, southeast, and west, with precision that rivals modern surveying instruments. Some researchers propose additional alignments with Orion's belt, a constellation that held spiritual significance in Egyptian cosmology. Chichen Itza's El Castillo Pyramid in Mexico aligns with equinoxes, casting serpent shadows on the pyramid steps during specific dates when day and night achieve equal length. Machu Picchu's temples in Peru align with sunrise and mountain peaks, creating sight lines that mark celestial and terrestrial features simultaneously. Puma Punku's gateway displays proportions and orientations, suggesting astronomical significance. These alignments span continents separated by thousands of kilometers and centuries separated by centuries of time. The probability of random alignment decreases dramatically with each additional example. Imagine flipping a coin and having it land heads. The probability is 50%. Flip it twice and get heads both time, probability drops to 25%. Continue this pattern and the probability becomes vanishingly small. When structures built by unconnected civilizations, separated by vast distances and centuries, all demonstrate celestial alignment, coincidence becomes implausible. The mathematical probability approaches zero. Instead, evidence suggests something more profound: sophisticated astronomical observation and mathematical knowledge shared across cultures or developed independently through similar intellectual processes. How did ancient astronomers acquire such knowledge? The answer lies in patient, systematic observation. Tracking celestial cycles requires watching the sky carefully across years and decades. The summer solstice, The day when the sun reaches its northernmost point and days are longest occurs at a consistent date each year. The winter solstice, when the sun reaches its southernmost point and days are shortest, also occurs predictably. Observing these extremes across multiple years allows prediction of their recurrence. An observer who marks the sun's rising point on the horizon each day will notice it shifts gradually northward from winter to summer, then southward again. After tracking this cycle for a full year, the pattern becomes clear. After tracking it for multiple years, the precision increases. The lunar cycle presents greater complexity. The moon's rising point on the horizon shifts gradually across an 18.6-year cycle. Understanding this cycle required observations spanning decades, suggesting communities committed to sustained astronomical study. The 19-year Metonic cycle, which reconciles lunar and solar calendars, was known to multiple ancient cultures. This cycle describes how 19 solar years approximately equal 235 lunar months, allowing lunar and solar calendars to remain synchronized. Understanding this relationship requires sophisticated mathematical knowledge and centuries of observation. Yet evidence suggests that ancient astronomers in different regions independently discovered or inherited knowledge of this cycle. The precession of equinoxes presents an even greater observational challenge. Earth's rotational axis gradually shifts, causing the position of stars to change relative to Earth's horizon across centuries. The precession cycle spans approximately 26,000 years. Detecting precession requires observations across centuries, comparing star positions recorded by earlier astronomers with current observations. Some classical astronomers, including Hipparchus in ancient Greece, understood precession. Yet how this knowledge was acquired remains unclear. The observations required would span generations, suggesting knowledge transmission systems capable of preserving astronomical data across centuries. Why invest such extraordinary effort in astronomical alignment? Several theories have been proposed. Religious significance offers one explanation. Connecting earthly structures to cosmic order may have held profound spiritual meaning. Temples aligned with solstices could represent humanity's relationship with divine cosmic forces. The precision of alignment might reflect religious devotion, the effort invested in perfect alignment demonstrating commitment to spiritual principles. Practical applications offer another explanation. For agricultural societies, understanding seasonal cycles was essential. Planting and harvest times depended on seasonal changes marked by celestial events. A structure that accurately marked solstices could serve as a calendar visible to entire communities. Farmers could observe when the sun's rising point reaches specific markers on the horizon, indicating planting time or harvest time. This dual-function spiritual significance, combined with practical utility, may explain why astronomical alignment appears so consistently across cultures. How did knowledge transfer between distant civilizations? This question becomes increasingly intriguing as we recognize the consistency of astronomical knowledge. Did astronomical understanding develop independently in multiple locations, with different civilizations discovering similar principles through similar observational processes? Or does evidence suggest contact networks we haven't yet identified? The precision of alignments suggests deliberate calculation rather than approximation. The consistency across cultures suggests either widespread knowledge, transmission, or independent discovery of similar principles. Some researchers propose that trade networks facilitated knowledge exchange. Phoenician traders traversed Mediterranean and Atlantic coasts. Indian Ocean trade routes connected Africa, Arabia, India, and Southeast Asia. Silk Road networks linked China, Central Asia, and the Mediterranean. These networks may have facilitated knowledge exchange alongside material goods. A merchant traveling between distant regions might have encountered different astronomical traditions, carrying knowledge back to his home civilization. Over generations, such exchanges might have spread astronomical knowledge across vast distances. Other researchers propose earlier contact between distant civilizations. The similarities between certain architectural features, pyramids appearing in both Egypt and Mesoamerica, for example, raise questions about possible influence or shared origins. Yet mainstream scholarship attributes these similarities to independent development, suggesting that pyramid construction represents a logical solution to monumental building challenges that different civilizations might discover independently. This remains debated, but the principle of independent discovery has merit. When faced with similar problems and similar resources, different societies might develop similar solutions. The precision of astronomical alignments in ancient structures reveals minds engaged in systematic observation and mathematical reasoning. This suggests intellectual traditions more sophisticated than conventional archaeology has acknowledged. The builders of these monuments possessed not just practical engineering knowledge, but theoretical understanding of celestial mechanics. They understood that celestial events occur predictably, that observations can be recorded and compared, that mathematical relationships underlie celestial cycles. This represents abstract thinking of considerable sophistication, the ability to recognize patterns, predict future events based on past observations, and translate abstract knowledge into concrete architectural design. Astronomical alignments in ancient structures reveal minds engaged in systematic observation and mathematical reasoning, suggesting intellectual traditions more sophisticated than conventional archaeology has acknowledged. The consistency of astronomical orientation across cultures raises profound questions about human intellectual capability and the transmission of knowledge across time and space. Whether through contact networks, independent discovery, or some combination of both, ancient peoples developed sophisticated understanding of celestial mechanics and incorporated this understanding into their most important monuments. This suggests that astronomy held central importance in ancient worldviews, not as peripheral curiosity, but as fundamental to understanding humanity's place in the cosmos. From these celestial alignments, we now turn to examining the construction techniques themselves, exploring how ancient builders translated astronomical knowledge and architectural vision into physical reality. Construction techniques solving the puzzle. We've explored the astronomical knowledge embedded in ancient monuments and recognized the consistency of celestial alignments across cultures. Now we turn to a more practical question. How were these structures actually built? What methods did ancient builders employ to move, shape, and position stones of extraordinary weight and size? Experimental archaeology has provided valuable insights into these questions, revealing both the ingenuity of ancient techniques and the limits of our current understanding. Over the past several decades, researchers have conducted systematic experiments to reconstruct ancient construction methods. Teams have successfully moved multi-ton stones using techniques reconstructed from archaeological evidence and logical inference. These experiments employ wooden sledges, water lubrication, to reduce friction lever systems, employing principles of mechanical advantage and organized labor coordinated through systematic planning. The Journal of Archaeological Science and other peer-reviewed publications have documented these experiments, providing quantitative data about feasibility and labor requirements. One well-documented study demonstrated that 150 people could transport a 4-ton block across level terrain, using these methods with the stone moving on a wooden sledge lubricated with water. The experiment required sustained effort, but proved feasible without requiring assumptions about lost technology or superhuman capability. For Stonehenge's bluestones, researchers proposed a water transport route that combines practical logistics with archaeological evidence. The stones were quarried in the Preseli Mountains of Wales. From there they were loaded onto wooden rafts constructed from timber available in the region. These rafts floated down Welsh rivers toward the coast, then crossed the Bristol Channel, a body of water separating Wales from England. Upon reaching English shores, the stones were transferred to additional rafts and transported up English rivers toward the Salisbury Plain. Once the rivers became too shallow for further navigation, the stones were unloaded and transported overland using sledges and organized labor teams. Experimental trials confirmed the feasibility of this route, though logistical challenges remained substantial. The coordination required constructing rafts timing river transport to avoid seasonal flooding. Managing transfers between water and land transport suggests sophisticated planning and resource management. For Egyptian pyramids, archaeological evidence and experimental work suggest workers used ramp systems to move massive blocks. Quarry marks show systematic extraction patterns indicating organized, methodical quarrying rather than haphazard stone removal. Papyri discovered in Egypt describe organized labor forces, provisioning systems, and administrative oversight of construction projects. These documents mention worker teams with names, ration allocations, and supervisory hierarchies. The Great Pyramid contains approximately 2.3 million blocks, averaging 2.5 tons each. Using ramp systems, whether straight, zigzag, or spiral configurations, teams of workers could move these blocks incrementally upward. The scale remains impressive, yet the methods appear achievable with available resources and sufficient labor coordination. Yet significant gaps persist in our understanding. How were the largest blocks, those exceeding 100 tons, moved? As stone size increases, proposed methods become increasingly speculative. Some researchers suggest counterweight systems where descending weights could provide mechanical advantage for lifting ascending stones. Others propose elaborate lever configurations, using fulcrums and mechanical principles to amplify human force. These theories have merit, but direct archaeological evidence remains limited. For Baalbek's 900-ton blocks, even theoretical explanations strain credibility. Moving a stone of this mass across 900 meters of terrain would require either enormous labor forces, possibly thousands of workers, or technological solutions we haven't yet identified. The precision of placement suggests not experimentation, but confident execution, implying builders possessed experience or knowledge we haven't fully reconstructed. The precision of stone fitting at sites like Puma Punku and Machu Picchu suggests advanced measurement tools and mathematical knowledge. Researchers have identified evidence of plumb bobs, weighted strings used to establish vertical alignment, levels for determining horizontal planes, and measuring rods for establishing distances. These tools, constructed from simple materials like wood and stone, allowed builders to achieve remarkable precision. Mathematical understanding of geometry and proportion is evident in architectural proportions and astronomical alignments. The builders understood not just how to move stones, but how to position them with accuracy sufficient for astronomical alignments to function across centuries. Consider the practical implications of stone-fitting precision. At Puma Punku, blocks fit together so precisely that a knife blade cannot slip between them. This required measurements accurate to millimeters. Each block was individually shaped to fit its neighbors. This suggests quality control systems, ensuring that each stone met specifications before being transported to its final position. Mistakes would be costly. A poorly fitted stone might compromise the entire structure. The consistency of precision across hundreds of stones suggests formal training systems master craftspeople, directing work and apprentices learning techniques through practice and instruction. What remains unclear is whether builders possess technological solutions we've lost, or whether their methods, though achievable with available resources, required organizational capabilities we underestimate. The evidence suggests the latter explanation has merit. Ancient societies possessed sophisticated systems for organizing, labor managing resources, and maintaining knowledge across generations. These organizational capabilities, developed for agricultural and administrative purposes, could be applied to construction projects. The investment of enormous resources in monuments suggests that these projects held profound significance, spiritual, political, or both, justifying the effort and resource commitment. Imagine standing at a pyramid construction site in ancient Egypt. Thousands of workers move in coordinated patterns. Some quarry stones using copper tools and stone hammers to extract blocks from bedrock. Others shape stones, smoothing surfaces and creating precise angles. Still others operate sledges, moving stones across sand lubricated with water. Supervisors coordinate activities, ensuring that materials arrive when needed, and that work proceeds according to plan. Food and water are distributed to workers. Tools are maintained and replaced. The entire operation functions as an integrated system, with each component contributing to the larger whole. This level of organization, sustained across years or decades, represents sophisticated management capability. The precision of these construction methods wouldn't be matched again until the Industrial Revolution, thousands of years later. Even today, with laser levels and computer modeling, engineers marvel at what was achieved with copper tools and rope. This recognition shouldn't lead us to assume lost technology or superhuman capability. Instead, it should inspire respect for the ingenuity, patience, and organizational sophistication of ancient peoples. They solved extraordinary problems using available resources and intellectual capabilities. Their solutions may differ from modern approaches, but they were no less effective. Experimental archaeology validates many proposed construction methods, yet the largest structures suggest either lost technologies or organizational sophistication that challenges our assumptions about ancient societies. The evidence indicates that ancient builders possessed knowledge and capability sufficient to accomplish what they did. Whether they possessed additional knowledge we've lost remains an open question. What seems clear is that we've underestimated the organizational and intellectual capabilities of ancient civilizations. The monuments themselves stand as evidence of what was possible when societies invested enormous resources in shared projects, guided by shared vision, and sustained across generations. From these practical construction methods, we now turn to examining the labor systems and social organization that made such projects possible. The labor question: organization and motivation. We've examined the construction techniques ancient builders employed and recognized the sophistication of their methods. Yet understanding how something was built raises a more fundamental question. Why did people invest such extraordinary effort in these projects? What motivated sustained commitment across generations? The answer reveals something profound about human nature and the societies that built these monuments. Building Stonehenge required sustained effort across 1,500 years. Multiple generations of workers quarried stones, transported them across vast distances, and positioned them with precision. The Great Pyramid's construction involved approximately 100,000 worker years of labor, meaning if 100,000 people worked simultaneously for 1 year, or 10,000 people worked for 10 years, or some combination totaling this magnitude. Easter Island's Moai production required coordinated effort across approximately 600 years, with hundreds of workers engaged in quarrying, carving, and transporting statues. These scales demand explanation. What motivated such sustained commitment? What social structures enabled organizing labor on this scale? what beliefs or values justified investing resources in monuments rather than in other pursuits. Conventional historical models propose coercion slave labor driven by authoritarian rulers who commanded obedience through force. This explanation has intuitive appeal. Powerful rulers could compel subjects to work, extracting labor through coercion rather than persuasion. Yet archaeological evidence complicates this picture significantly. Skeletal remains of pyramid workers discovered near construction sites show no signs of systematic abuse or malnutrition. Instead, bones display evidence of medical care and adequate nutrition. Fractures were treated. Infections were managed. Workers received health care suggesting they were valued rather than disposable. Workers' villages discovered near pyramid sites reveal organized provisioning bakeries, producing bread for workers, storage facilities, holding grain, administrative systems, tracking rations. This evidence suggests valued labor rather than exploited slavery. Alternative models propose religious motivation. Workers engaged in sacred projects believed to serve cosmic purposes or ensure afterlife benefits. For Egyptian workers, participation in pyramid construction may have represented service to divine pharaohs with spiritual rewards, justifying the effort. For Stonehenge builders, participation in an astronomical observatory may have connected them to cosmic order, providing spiritual significance to their labor. This would explain sustained effort without requiring coercion. Workers would participate willingly because they believed in the project's spiritual importance. Seasonal labor systems may have mobilized agricultural populations during off-seasons, combining practical and spiritual motivations. Agricultural societies experience seasonal variation in labor demands. Planting and harvest seasons require intensive effort. Winter months offer reduced demands. Monument construction could have occurred during these low-demand periods, mobilizing workers who would otherwise be idle. This system would provide practical benefits utilizing available labor while allowing workers to maintain agricultural activities. The spiritual significance of projects would provide additional motivation beyond economic necessity. Social cohesion may have driven participation in ways we often underestimate. Monumental construction projects create shared identity and purpose. Participating in a multi-generational project, knowing one's work contributes to something larger than individual life, may have provided meaning and status. Archaeological evidence of feasting sites near construction areas suggests communal celebration accompanying labor. Workers gathered for meals, possibly for festivals or ceremonies, honoring the work. These gatherings would strengthen social bonds and reinforce shared commitment to the project. The experience of working collectively toward a shared goal, celebrated through communal feasting, would create powerful social cohesion. Consider the psychological dimensions of participation. A worker contributing to Stonehenge's construction knew that his effort would be part of a structure that would endure for centuries. His grandchildren and their descendants would see the stones he helped position. This knowledge that one's work would persist beyond individual lifetime may have provided profound meaning. The worker wasn't simply laboring for immediate compensation, but contributing to something transcendent. This perspective transforms the nature of work from mere obligation to meaningful participation in something greater than self. The consistency of astronomical alignment across cultures suggests shared cosmological worldviews. Societies invested enormous resources in connecting earthly structures to celestial order, implying religious or philosophical frameworks that prioritize this alignment above other practical concerns. The decision to invest in astronomical alignment rather than in other practical improvements suggests that spiritual or philosophical values took precedence. This reveals societies organized around shared cosmological understanding worldviews that made monument construction seem essential rather than optional. Yet motivation likely varied across cultures and time periods. Pharaonic Egypt's centralized authority differed fundamentally from Easter Island's decentralized chiefdoms or Göbekli Tepe's hunter-gatherer communities. Different social structures produced different organizational outcomes. Egyptian pharaohs possessed centralized authority enabling command of vast labor forces. Easter Island's chiefs possessed authority within their communities but lacked the centralized power of pharaohs. Göbekli Tepe's hunter-gatherers lacked centralized authority entirely, yet still organized substantial construction projects. This suggests that different social structures could motivate monumental construction through different mechanisms: coercion in centralized states, social prestige in chiefdoms, spiritual commitment in egalitarian communities. The evidence suggests that motivation was multifaceted and context-dependent. Practical considerations mattered. Workers needed food and shelter. Spiritual considerations mattered. Workers believed in the project's significance. Social considerations mattered. Workers gained status and identity through participation. Political considerations mattered. Rulers demonstrated power through monumental construction. Economic considerations mattered. Construction projects mobilized labor and resources. All these factors likely operated simultaneously, creating complex motivational landscapes that varied across cultures and time periods. What emerges from this analysis is a picture of ancient societies more nuanced than simple hierarchical models propose. Workers weren't merely passive recipients of commands, but participants in projects they believed in. Rulers weren't merely despots extracting labor, but leaders mobilizing shared commitment toward shared goals. Societies weren't merely organized through coercion, but through combinations of practical necessity, spiritual belief, social cohesion, and political authority. The monuments themselves represent not just displays of power, but expressions of shared values and worldviews. Ancient construction reveals sophisticated labor organization and complex motivations combining practical, spiritual, and social dimensions, suggesting societies more nuanced than simple hierarchical models propose. Understanding why people built these monuments requires understanding their worldviews, their social structures, and their beliefs about meaning and purpose. The monuments endure not just as engineering achievements, but as evidence of human capacity for sustained cooperation toward shared goals. From these insights into labor and motivation, we now turn to examining the knowledge systems that guided ancient builders, exploring what intellectual traditions may have been lost across centuries. Lost knowledge. What did we forget? We've explored the labor systems and motivations that drove ancient construction. Now we confront a more unsettling question. What knowledge did ancient civilizations possess that we've lost? The consistency of astronomical knowledge across unconnected civilizations raises intriguing questions about knowledge transfer and the fragility of intellectual traditions. Understanding what may have been lost requires examining both the evidence of contact between ancient peoples and the mechanisms through which knowledge disappears across time. The consistency of astronomical knowledge across unconnected civilizations raises fundamental questions about knowledge transfer. Did independent discovery account for widespread astronomical understanding, or does evidence suggest contact networks facilitating knowledge exchange? This question has occupied scholars for decades, generating substantial debate. The evidence points in multiple directions simultaneously. Some astronomical knowledge, understanding of solstices and equinoxes, could be discovered independently by any civilization with systematic observation capabilities. Other knowledge, understanding of the metonic cycle or precession of equinoxes, requires observations spanning decades or centuries, suggesting either independent discovery by multiple civilizations or knowledge transmission across networks. The Antikythera mechanism provides a striking example of technological sophistication that seemed anomalous until further investigation revealed its significance. This device, recovered from a shipwreck off the Greek island of Antikythera in 1901, is an ancient astronomical calculator constructed from bronze gears. Dating to approximately 100 BCE, the mechanism contains at least 30 interlocking gears designed to predict astronomical positions and lunar eclipses. The sophistication of the device, its precision, engineering and mathematical principles seem to exceed what scholars expected from ancient Greek technology. Yet further research revealed that similar devices may have existed in other ancient cultures. The Antikythera mechanism wasn't an anomaly, but evidence of a technological tradition we'd underestimated. Trade networks connected ancient civilizations more extensively than once believed. Phoenician traders traversed Mediterranean and Atlantic coasts, establishing trading posts and facilitating exchange of goods and ideas. Indian Ocean trade routes connected Africa, Arabia, India, and Southeast Asia, enabling commerce and cultural exchange across vast distances. Silk Road networks developing over centuries linked China, Central Asia, and the Mediterranean, facilitating not just material trade, but transmission of ideas, technologies, and knowledge. These networks may have facilitated knowledge exchange alongside material goods. A merchant traveling between distant regions might encounter different astronomical traditions, different mathematical systems, different architectural approaches. Returning home, such a merchant might carry knowledge that influenced his own civilization's development. Some researchers propose earlier contact between distant civilizations than conventional chronologies suggest. Similarities between Sumerian and Egyptian writing systems, though debated among scholars, suggest possible influence or shared origins. Both civilizations developed writing systems around similar time periods, yet the systems differ substantially. Some researchers propose that contact or cultural influence may have played a role in their development. However, mainstream scholarship attributes these similarities to independent development, suggesting that writing systems represent logical solutions to communication problems that different civilizations might discover independently. The debate remains unresolved, illustrating how difficult it is to distinguish between independent discovery and knowledge transmission. Architectural parallels between Egyptian pyramids and Mesoamerican pyramids raise similar questions. Both civilizations constructed pyramid-shaped structures, yet separated by thousands of kilometers and centuries of time. Did one civilization influence the other? Did knowledge transmission occur through contact networks? Or did both civilizations independently discover that pyramid construction represented a logical approach to monumental building? Mainstream scholarship favors independent development, noting that pyramid construction represents a relatively straightforward architectural solution. Stack stones in progressively smaller layers until reaching a point. Yet the consistency of pyramid construction across cultures raises questions worth considering. The mathematical sophistication evident in multiple cultures, understanding of pi geometric progressions and astronomical cycles suggests either independent discovery or transmitted knowledge. Multiple ancient civilizations possessed sophisticated mathematical knowledge. Egyptian mathematicians understood geometric principles and could calculate areas and volumes. Babylonian mathematicians developed sophisticated algebraic systems. Chinese mathematicians developed advanced computational methods. Indian mathematicians developed the decimal system and zero. These mathematical traditions developed in different regions, yet share fundamental principles. This consistency could reflect independent discovery of mathematical truths. After all, geometric principles are universal. Or it could reflect knowledge, transmission through trade networks and cultural contact. What knowledge was lost? The question haunts historians and archaeologists. The Library of Alexandria, containing hundreds of thousands of texts, was destroyed through fire and conquest. Countless works on mathematics, astronomy, medicine, and philosophy vanished. The Spanish conquest of Mesoamerica resulted in destruction of Aztec and Maya codices, written records containing knowledge of astronomy, mathematics, and history. Conquistadors viewing these texts as heretical burned them. Oral traditions lacking written preservation vanish when speakers die. Knowledge transmitted through apprenticeship systems disappears when the chain of transmission breaks. We may possess only fragments of sophisticated intellectual traditions that flourished, then disappeared. Consider the implications. If the Library of Alexandria had survived intact, our understanding of ancient knowledge would be vastly different. If Maya codices had been preserved, we would possess detailed records of Mesoamerican astronomy and mathematics. If oral traditions had been recorded, we would understand knowledge systems that shaped ancient societies. The loss of these knowledge sources means we're working with incomplete information, trying to reconstruct sophisticated intellectual traditions from fragmentary remains. Some researchers propose cyclical civilizational patterns, periods of advancement followed by collapse and knowledge loss. This model, though speculative, would explain technological sophistication appearing seemingly without precedent. A civilization might develop sophisticated knowledge, then collapse due to environmental degradation, warfare, or other factors. The knowledge would be lost, preserved only in fragmentary form in monuments or oral traditions. A later civilization discovering these monuments might struggle to understand how they were built, lacking the knowledge systems that guided their construction. This cyclical model remains speculative, and evidence remains limited. Yet the possibility warrants consideration, given the patterns we observe in the archaeological record. The question of knowledge transmission and loss becomes particularly intriguing when we consider that sophisticated knowledge may have developed and disappeared repeatedly throughout human history. We possess evidence of advanced civilizations that collapsed: the Maya civilization, the Indus Valley civilization, Easter Island society. Each collapse likely involved loss of knowledge as social structures disintegrated. If this pattern repeated across human history, we might be discovering only the most recent cycle of advancement and collapse, with earlier cycles leaving only fragmentary evidence. How did knowledge transfer between distant civilizations? This remains one of archaeology's most challenging questions. Direct evidence of contact is often lacking. We infer contact from similarities in artifacts, technologies, or ideas. Yet similarity can result from independent discovery as easily as from contact. Distinguishing between these possibilities requires careful analysis and often remains ambiguous. Evidence suggests knowledge transmission networks and possible lost intellectual traditions, though distinguishing fact from speculation requires rigorous evidence and methodological caution. The consistency of astronomical knowledge across cultures suggests either widespread contact networks or independent discovery of similar principles. The sophistication of ancient technologies like the Antikythera mechanism suggests intellectual traditions more advanced than we often acknowledge. The destruction of libraries and codices suggests substantial knowledge loss. Yet we must be cautious about speculation. Without direct evidence, we cannot definitively claim knowledge, transmission, or lost technologies. What we can say is that the possibility exists that evidence suggests it may have occurred, and that future discoveries may illuminate these questions. From these considerations of lost knowledge, we turn now to examining the mysteries that remain unsolved despite centuries of investigation. Mysteries that remain. We've examined lost knowledge and the mechanisms through which information disappears across time. Yet despite centuries of investigation and modern archaeological advances, ancient megastructures retain fundamental mysteries that continue to perplex researchers. These aren't minor puzzles, but core questions about why these monuments were built, how knowledge persisted across generations, and what purposes they ultimately served. Confronting these enduring mysteries offers perspective on the limits of our understanding. Why were certain sites chosen for construction? This question appears simple, yet resists straightforward answers. Stonehenge's location on the Salisbury Plain offers no obvious practical advantages. The site sits on exposed terrain, without natural shelter or abundant water sources. Yet builders invested enormous effort in this specific location, transporting materials across vast distances. Theories range from sacred geography, the site possessing spiritual significance and local cosmology, to astronomical sightlines, the location offering optimal views of celestial events, to geological properties we haven't yet identified. Some researchers propose that the site's location, relative to other sacred sites, formed a larger landscape of spiritual significance. Others suggest that the Salisbury Plain's chalk geology provided specific advantages for construction or ritual purposes. Yet definitive explanations remain elusive. Göbekli Tepe's hilltop location presents similar puzzles. The site sits on a limestone plateau in southeastern Turkey, elevated above surrounding terrain. This location required transporting water and resources uphill, complicating logistics. Yet builders chose this specific location for their temple complex. Why theories propose that the elevated position offered symbolic significance, connecting the temple to the heavens. Others suggest that the location provided visibility across surrounding landscape, allowing ceremonial gatherings to be observed from distance. Still others propose that the hilltop's geology offered specific advantages for construction. The evidence remains insufficient to determine which explanation is correct. Baalbek's high-altitude temple served a limited population. The site sits in Lebanon's Bekaa Valley at elevation, where climate limits agricultural productivity. Yet Romans invested enormous resources in constructing a massive temple complex at this location. The practical justification for such investment remains unclear. Religious significance likely played a role. The site may have held sacred meaning in local cosmology. Yet the scale of construction seems disproportionate to the population that could have supported it. This raises questions about whether the temple served primarily local populations or attracted pilgrims from distant regions. How was knowledge transmitted across generations, spanning centuries? This question becomes particularly acute when considering projects requiring sustained effort across timescales exceeding individual lifespans. Stonehenge's construction required approximately 1,500 years of sustained effort. Easter Island's Moai production spanned roughly 600 years. How did knowledge of construction techniques, astronomical alignments, and organizational systems persist across such timescales without written records? Oral traditions, apprenticeship systems, and ritual practices may have preserved knowledge. A master builder would train apprentices, transmitting techniques through practice and instruction. Ritual ceremonies might have reinforced astronomical knowledge, ensuring that celestial alignments remain significant across generations. Yet direct evidence of these knowledge transmission systems remains limited. We infer their existence from the consistency of construction methods and astronomical alignments, but we lack detailed records of how knowledge was actually preserved and transmitted. What purposes did these structures serve beyond their apparent functions? This question invites us to consider that we may be misunderstanding the primary purposes of ancient monuments. Were they temples, observatories, calendars, or something else entirely? Evidence suggests multiple, simultaneous functions. Stonehenge served as burial ground, ceremonial center, and astronomical calculator. The site contains cremated remains of hundreds of individuals, indicating ritual burial practices. yet it also aligns with celestial events, suggesting astronomical observation, and its arrangement suggests ceremonial gathering spaces. Rather than serving a single function, the monument appears to have served multiple purposes simultaneously. Yet we may be missing primary purposes that shape the monument's design. What if Stonehenge's primary purpose was something we haven't yet identified, perhaps a healing center as some theories propose, or a place of initiation into spiritual mysteries? The evidence we possess may not be sufficient to determine the full range of purposes the monument served. Why did construction cease? This question becomes particularly poignant when considering projects abandoned before completion. Easter Island's Moai production stopped abruptly around 1600 CE. Hundreds of statues remain incomplete in quarries abandoned mid-carving. What events prompted this sudden cessation? Environmental degradation, deforestation, reducing available resources likely played a role. Social disruption, warfare, and societal collapse appears evident in the archaeological record. Yet the exact sequence of events remains unclear. Göbekli Tepe presents an even more puzzling case. The site was deliberately buried with structures intentionally filled with earth and stone. Why would builders deliberately bury a temple complex they'd invested such effort in constructing? Was this a ritual act burying the sacred site as part of religious practice? Was it practical protecting the site from damage? Or did it represent abandonment, with later peoples burying the site to remove it from view? The evidence remains fragmentary, insufficient to determine the builder's intentions. Could undiscovered sites exist? This question becomes increasingly relevant as technology advances. Aerial surveys and satellite imaging continue revealing previously unknown structures. LiDAR technology, using laser pulses to penetrate vegetation, has identified hidden Mesoamerican cities beneath jungle canopy. In Cambodia, LiDAR surveys revealed extensive medieval cities, previously unknown to modern archaeology. How many ancient monuments remain undiscovered, buried beneath earth or ocean? Archaeological surveys have covered only a fraction of Earth's surface. Vast regions remain unexplored or inadequately surveyed. Underwater archaeology has barely begun exploring submerged landscapes. As sea levels rose following the last ice age, coastal settlements were inundated. How many ancient monuments lie beneath ocean waves waiting for discovery? The possibility of major discoveries remains substantial. Consider the implications of undiscovered sites. If we discovered another Göbekli Tepe, a temple complex predating agriculture by thousands of years, our understanding of human development would shift dramatically. If we discovered astronomical observatories predating known civilizations, our understanding of knowledge transmission would require revision. If we discovered written records from lost civilizations, we would possess direct evidence of knowledge systems we can currently only infer. The monuments we've discovered may represent only a fraction of what ancient peoples constructed. Our understanding of ancient capabilities may be limited by the accidents of preservation and discovery. Despite archaeological advances, ancient megastructures retain mysteries that humble our understanding, suggesting layers of meaning and purpose we've yet to fully comprehend. The monuments themselves stand as evidence of human ingenuity and ambition, yet they also stand as reminders of how much we don't know about the past. Each answer we discover raises new questions. Each mystery we solve reveals additional mysteries beneath it. This pattern suggests that our understanding of ancient civilizations remains incomplete. The monuments invite continued investigation, promising that future discoveries may illuminate questions that currently perplex us. They remind us that human history extends far deeper than written records, and that civilizations of considerable sophistication flourished long before the historical period we typically study. From these enduring mysteries, we now turn to examining the broader implications of ancient megastructures for understanding human nature and civilization itself. Perspectives from the builders. We've explored the enduring mysteries surrounding ancient monuments and recognized how much remains unknown despite centuries of investigation. Yet we can approach these structures from another angle, not asking what the monuments tell us about ancient capabilities, but rather asking what they reveal about the people who built them. What do we know about the builders themselves, and how did they understand their own work? We possess limited direct evidence of builders' perspectives. Few written records survive from the societies that created these structures. The vast majority of ancient peoples left no written accounts of their thoughts, beliefs, or motivations. Yet archaeological evidence provides glimpses into builders' minds and values. Graffiti discovered in Egyptian pyramids preserves workers' names and team identities. Workers carved their names into stone blocks, leaving traces of individual identity within monumental structures. Papyri discovered in Egypt describe administrative systems, labor organization, and resource allocation. These documents reveal how construction projects were managed, how workers were provisioned, and how knowledge was organized. Oral traditions recorded by later generations preserve memories of construction. Stories passed down through centuries contain kernels of historical information, though distinguishing fact from legend requires careful analysis. The builders possessed sophisticated understanding of mathematics, astronomy, and engineering. This wasn't intuitive knowledge acquired through casual observation, but learned expertise, suggesting formal training systems and knowledge specialists. The precision of astronomical alignments indicates that builders understood celestial mechanics with considerable sophistication. The accuracy of geometric proportions indicates mathematical knowledge. The structural stability of monuments indicates engineering understanding. This expertise didn't emerge spontaneously, but developed through systematic learning and practice. Master builders directed projects possessing knowledge and authority to make decisions about construction methods and design. Apprentices learned techniques through practice and instruction, acquiring skills through years of training. Laborers executed plans performing the physical work of quarrying, transporting, and positioning stones. This hierarchical knowledge structure implies educational institutions we haven't yet identified. Where did master builders learn their craft? How was knowledge transmitted from experienced builders to apprentices? What institutions or systems preserved and transmitted technical knowledge? The evidence suggests sophisticated educational structures, yet we lack detailed records of how these systems functioned. The builders understood their work as sacred or cosmically significant. Astronomical alignments suggest cosmological worldviews in which earthly structures reflected celestial order. The investment of enormous resources in precise astronomical alignment indicates that builders believed this alignment held profound importance. Religious inscriptions and ritual deposits suggest spiritual frameworks motivating construction. At many sites, archaeologists have discovered ritual objects, offerings, ceremonial deposits, sacred items, suggesting that construction was accompanied by religious practice. The builders weren't merely executing practical projects, but participating in sacred endeavors. Their work held spiritual significance beyond practical utility. The builders possessed aesthetic sensibilities. The proportions of Egyptian temples demonstrate understanding of harmony and balance. The symmetry of Stonehenge suggests appreciation for geometric beauty. The artistic detail of Easter Island Moai, the careful carving of facial features and body proportions, suggests aesthetic vision. These features exceed what practical function would require. A temple doesn't need perfect proportions to shelter worshippers. A monument doesn't need artistic detail to mark astronomical events. The investment in aesthetic refinement suggests that builders and their societies valued beauty and meaning alongside practical concerns. This reveals cultures sophisticated enough to pursue aesthetic goals even when practical necessities might have sufficed. The builders understood their work as legacy. Multi-generational projects suggest awareness that individual effort contributed to something transcending individual lifespans. A worker contributing to Stonehenge's construction knew that his effort would be part of a structure that would endure for centuries. His grandchildren and their descendants would see the stones he helped position. This knowledge that one's work would persist beyond individual lifetime shaped motivation and meaning-making. The builder wasn't simply laboring for immediate compensation, but contributing to something that would outlast him. This temporal perspective, understanding oneself as part of a continuum extending backward and forward through time, represents sophisticated consciousness about human existence and legacy. Consider what this reveals about ancient peoples' understanding of time and meaning. They recognized that individual lives were brief, but that human communities persisted across generations. They invested resources in projects that wouldn't be completed during their lifetimes, trusting that future generations would continue the work. This suggests hope, commitment to shared values, and belief in continuity across time. It suggests that ancient peoples possessed not just practical knowledge, but philosophical understanding of human existence and meaning. Yet we cannot fully access builders' consciousness. We interpret through modern frameworks, potentially misunderstanding their intentions and meanings. We assume that astronomical alignments held significance because we value astronomy. But what if builders understood these alignments differently than we do? We assume that aesthetic refinement reflected cultural values. But what if builders pursued beauty for reasons we haven't considered? We interpret monuments through our own worldviews, potentially projecting modern meanings onto ancient structures. The monuments remain, but their builders' inner lives remain partially obscured by time. We can infer motivations from evidence, but we cannot know with certainty what builders thought or felt. Yet this limitation itself is instructive. It reminds us that ancient peoples possess depths we continue discovering. Each generation of archaeologists reinterprets ancient monuments through contemporary frameworks, revealing new meanings. The monuments invite continued investigation precisely because they resist complete understanding. They stand as evidence of human creativity and ambition, yet also as reminders of how much we don't know about the past. The builders emerge as sophisticated, motivated individuals, engaged in meaningful work within complex social and spiritual frameworks, reminding us that ancient peoples possessed intellectual and emotional depths we continue discovering. They weren't simply following orders or performing rote labor. They were participating in projects they believed in, guided by worldviews that made monument building seem essential. They possessed knowledge systems capable of organizing complex projects and transmitting information across generations. They valued beauty, meaning, and legacy alongside practical concerns. They understood themselves as part of communities extending across time. These characteristics suggest that ancient builders were fundamentally similar to modern humans, possessed of similar intellectual capabilities, similar capacity for meaning-making, similar desire to create something that would outlast them. From these insights into builders' perspectives, we now turn to examining the broader patterns connecting these monuments across cultures and time. Connections and patterns. We've examined individual builders and recognized their sophistication and motivation. Now we step back further, observing patterns that connect monuments across vast distances and centuries. When we compare megastructures from different cultures and time periods, a striking consistency emerges, one that suggests something fundamental about human nature and the universal impulses that drive civilization. A striking pattern emerges when examining ancient monuments globally across continents and centuries. Societies invested enormous resources in monumental construction. The impulse appears universal, not limited to particular cultures or time periods, but recurring across human societies separated by geography and time. From Neolithic Göbekli Tepe in Turkey, constructed 11,500 years ago, to classical Rome, building temples and structures, to pre-Columbian Americas, constructing pyramids and ceremonial centers, societies built structures exceeding practical necessity. This consistency across such vast temporal and geographic spans suggests something more than coincidence. It suggests a fundamental human impulse toward monumental construction. These monuments share striking characteristics despite their geographic and temporal separation. Most align with celestial events, solstices, equinoxes, star positions, lunar cycles. Most required sophisticated labor organization, coordinating hundreds or thousands of workers across years or decades. Most served religious or ceremonial functions alongside practical purposes. Most demonstrated mathematical and astronomical knowledge. Most were built to endure, constructed with materials and techniques designed for permanence rather than temporary utility. A structure built to last centuries represents different priorities than one built for immediate use. The investment in durability suggests that builders believe their work would matter to future generations. This consistency suggests something fundamental about human nature. Across cultures, humans appear driven to create lasting monuments, to connect earthly structures to cosmic order, to organize collective effort toward shared purposes. This impulse transcends practical survival needs. A society could survive without monuments. Food production, shelter construction, and tool-making address immediate survival needs. Yet societies across the globe invested resources in monuments that served primarily spiritual or symbolic purposes. This suggests spiritual or philosophical dimensions to human consciousness that transcend practical concerns. Yet significant differences exist between monuments reflecting distinct cultural values and social structures. Egyptian pyramids emphasized individual rulers. Pharaohs built monuments to themselves, expressing personal power and divine status. Stonehenge served communal purposes with no evidence of individual rulers claiming the monument. Easter Island's Moai represented ancestors, suggesting cosmological systems centered on ancestral veneration. Göbekli Tepe's pillars depicted predators and dangerous animals, suggesting symbolic or spiritual significance, different from ancestor representation. Baalbek's massive foundation stones served primarily structural purposes, supporting temples built above them. Puma Punku's precisely fitted stones served aesthetic and symbolic purposes alongside structural function. These differences reflect distinct cultural values and social structures. The pattern suggests that, while the impulse to build monumentally appears universal, its expression varies dramatically based on cultural context. Egyptian pharaohs built pyramids because their society organized around individual rulers with divine status. Stonehenge builders created communal gathering spaces because their society organized around collective ritual. Easter Island builders created ancestor representations because their cosmology centered on ancestral connection. Understanding ancient structures requires understanding the specific societies that built them, not imposing a universal interpretations. Each monument reflects the particular worldview and social organization of the civilization that created it. Yet despite these differences, the consistency of astronomical alignment across cultures raises intriguing questions. Did independent discovery of astronomical knowledge occur repeatedly with different civilizations, discovering similar principles through similar observational processes, or does this consistency suggest transmitted knowledge with astronomical understanding spreading through trade networks or cultural contact? The answer remains debated among scholars. Some argue that astronomical knowledge represents logical conclusions that different civilizations might reach independently. Understanding that the sun's rising point shifts seasonally requires only patient observation. Any civilization with systematic observation capabilities might discover this. Others argue that the precision and sophistication of astronomical knowledge suggests transmission rather than independent discovery. The Metonic cycle, for example, requires observations spanning decades. Understanding precession requires observations spanning centuries. These achievements seem less likely to occur independently in multiple locations. The consistency of astronomical alignment might reflect both independent discovery and knowledge transmission. Some astronomical knowledge, understanding of solstices and equinoxes, might be discovered independently. Other knowledge, understanding of complex cycles, might be transmitted through contact networks. This mixed model would explain both the universal patterns and the variations we observe across cultures. Consider the implications of these patterns. If the impulse to build monumentally is universal, this suggests that humans across cultures share fundamental drives and values. Spiritual and philosophical concerns appear to transcend practical survival needs. The desire to create lasting monuments to connect to cosmic order, to organize collective effort toward shared purposes, appears across human societies. This suggests that human nature contains dimensions beyond practical utility, dimensions that drive us to create meaning, to connect to something larger than ourselves, to leave legacies that outlast our individual lives. Yet the expression of these universal impulses varies dramatically based on cultural context. The same fundamental human drives produce different monuments reflecting different worldviews. This suggests that while human nature may be universal, human culture is diverse. Understanding ancient societies requires recognizing both the universal, human impulses they express and the culturally specific ways they express them. Comparing megastructures across cultures reveals both universal human impulses and culturally specific expressions, suggesting that ancient societies possess both shared human nature and distinct worldviews. The monuments themselves stand as evidence of this dual nature, expressions of universal human drives shaped by particular cultural contexts. They reveal that ancient peoples, despite their different technologies and social organizations, grappled with similar fundamental questions about meaning, purpose, and humanity's place in the cosmos. From these broad patterns connecting monuments across cultures, we now turn to examining what these ancient structures can teach us about navigating modern challenges. Modern implications, what ancient builders can teach us. We've examined the patterns connecting ancient monuments across cultures and recognized both universal human impulses and culturally specific expressions. Now we turn to a more immediate question. What can these ancient structures teach us about our own time? What lessons do ancient megastructures offer for understanding human capability, knowledge systems, and the challenges facing modern civilization? Ancient builders demonstrate that sophisticated knowledge and organizational capability flourished without modern technology. This challenges common assumptions that progress requires industrial machinery, computers, and modern engineering tools. Instead, the evidence suggests that human ingenuity, mathematical understanding, and social organization represent the fundamental technologies underlying civilization. Modern machinery amplifies human capability, but it doesn't create capability from nothing. The capacity to solve complex problems, organize large-scale efforts, and transmit knowledge across generations existed long before industrial technology. This recognition invites us to reconsider what we mean by progress and technological advancement. Consider what ancient builders accomplished with available resources. They moved multi-ton stones across vast distances without wheeled vehicles or draft animals. They positioned stones with precision rivaling modern construction standards without laser levels or computer modeling. They tracked celestial cycles without telescopes or computers. They organized labor forces numbering in the thousands without modern communication systems. These achievements suggest that human capability, the ability to observe, calculate, plan, and execute, represents a more fundamental technology than the machines we've invented. Modern technology enhances these capabilities, but doesn't replace them. The sustainability question emerges forcefully from Easter Island's history. The island's environmental degradation, accompanying intensive monument construction, demonstrates that ancient societies faced ecological limits, just as modern civilization does. The collapse of Easter Island civilization from a thriving society to one facing resource, scarcity, and social disruption suggests that resource overexploitation produces consequences regardless of historical period. This parallel to modern environmental challenges suggests ancient societies grappled with sustainability, questions we continue facing today. Easter Island presents a cautionary narrative about the consequences of prioritizing short-term goals over long-term sustainability. The Rapa Nui people invested enormous resources in creating monuments that express their cultural identity and spiritual beliefs. Yet in doing so, they depleted the resources necessary for their civilization's survival. The statues that represented their culture's greatest achievement ultimately contributed to its decline. This pattern, civilizations consuming resources unsustainably and facing collapse, appears repeatedly in human history. Understanding Easter Island's trajectory offers perspective on modern challenges. We face similar choices investing resources in projects that express our values while maintaining the ecological systems that sustain us. The knowledge transmission question illuminates modern concerns about information preservation. Ancient societies preserved knowledge through oral tradition, apprenticeship systems, and ritual practices systems, vulnerable to disruption. The loss of knowledge when societies collapsed or when written records were destroyed demonstrates the fragility of intellectual traditions. The Library of Alexandria's destruction eliminated countless texts. Spanish conquest of Mesoamerica destroyed Maya and Aztec codices. Oral traditions vanished when speakers died. We may possess only fragments of sophisticated intellectual traditions that flourished, then disappeared. Modern digital systems, while robust in some ways, face different vulnerabilities. Data stored on servers can be lost through technical failure, natural disaster, or deliberate destruction. Digital formats become obsolete as technology evolves. Information stored in proprietary formats may become inaccessible when companies cease supporting those formats. The question of how to preserve knowledge across generations remains relevant despite modern technology. We've solved some problems. Digital storage allows vast quantities of information to be preserved, yet created new problems. How do we ensure that digital information remains accessible across centuries? How do we preserve knowledge in formats that will survive technological change? The motivation question challenges modern assumptions about labor and meaning. Ancient builders engaged in sustained effort, motivated by spiritual significance, social cohesion, and participation in projects transcending individual lifespans. They weren't primarily motivated by individual compensation or personal advancement. Instead, they participated in projects they believed in, guided by worldviews that made monument building seem essential. Modern labor systems emphasizing individual compensation and short-term productivity may underestimate human motivation for meaningful work and lasting contribution. Research in modern psychology and organizational behavior suggests that people are motivated not just by compensation, but by meaning, purpose, and connection to something larger than themselves. Workers engaged in meaningful projects show higher motivation and satisfaction than those performing purely instrumental tasks. The opportunity to contribute to something that will outlast individual lifespans provides motivation beyond financial reward. Ancient builders understood this intuitively. They invested effort in projects they believed in, motivated by spiritual significance and social cohesion. Modern organizations might benefit from recognizing these deeper motivations. The astronomical knowledge question suggests that understanding natural cycles and cosmic order held profound significance for ancient peoples. Modern civilization's disconnection from celestial cycles and seasonal patterns may represent loss rather than progress. Ancient peoples lived in intimate connection with natural cycles. They observed the sky, systematically tracked celestial events, and organized their activities around seasonal changes. This connection to natural rhythms shaped their worldviews and values. Modern civilization, with artificial lighting, climate control, and global supply chains, has largely disconnected from these natural cycles. We've gained convenience and control, yet perhaps lost something valuable in the process. The builder's integration of practical and spiritual knowledge suggests frameworks we might learn from. Ancient monuments served multiple purposes, simultaneously practical, spiritual, aesthetic, and social. This integration of different dimensions of human experience represents a different approach than modern specialization, which often separates practical concerns from spiritual or aesthetic ones. Reconnecting these dimensions might offer valuable perspectives for addressing modern challenges that require integrated thinking. Ancient megastructures remind us that human capability, knowledge, and meaning-making transcend particular technological eras, offering perspectives valuable for navigating modern challenges. The monuments stand as evidence that humans possess fundamental capabilities, the ability to observe, calculate, plan, organize, and create meaning that persist across technological change. Modern technology amplifies these capabilities, but doesn't replace them. Understanding what ancient peoples accomplished with available resources reminds us that human ingenuity and determination represent more fundamental technologies than the machines we've invented. The monuments also remind us that civilizations face choices about how to use their resources and capabilities. Ancient peoples made choices that reflected their values and worldviews, sometimes with consequences they didn't anticipate. Modern civilization faces similar choices. We possess unprecedented technological capability, yet we must choose how to use it. The lessons from ancient monuments about sustainability, knowledge preservation, meaningful work, and integration of different dimensions of human experience offer guidance as we navigate these choices. Ongoing research, what we're still discovering. We've examined what ancient monuments teach us about modern challenges and recognize that our understanding remains incomplete. Yet the story of ancient megastructures is far from finished. Contemporary research methods are generating new data and revealing insights that previous generations of archaeologists couldn't access. The technologies emerging in recent decades promise to transform our understanding of ancient civilizations in ways we're only beginning to appreciate. LiDAR technology has revolutionized archaeological survey in ways that seemed impossible just decades ago. LiDAR, which stands for light detection, and ranging, uses airborne laser scanning to penetrate vegetation and reveal structures hidden beneath jungle canopy or dense forest. The technology works by sending laser pulses from aircraft toward the ground and measuring how long the pulses take to return. Dense vegetation absorbs or reflects pulses, but some penetrate to the ground surface, revealing topography beneath the canopy. In Cambodia, LiDAR surveys identified extensive medieval cities beneath vegetation, revealing settlement patterns and urban organization previously unknown to modern archaeology. In Mesoamerica, LiDAR surveys continue revealing previously unknown pyramids and settlement patterns, suggesting that Maya civilization was far more extensive and densely populated than previously believed. Applied to known sites, LiDAR may reveal subsurface structures and modifications we've missed through conventional excavation. At Stonehenge, LiDAR surveys have identified previously unknown structures in the surrounding landscape, suggesting that the monument was part of a larger complex of ritual sites we're only now beginning to understand. Isotope analysis provides unprecedented detail about ancient populations. Oxygen and strontium isotopes in skeletal remains reveal geographic origins of individuals, illuminating trade networks and population movement. Different regions have distinctive isotopic signatures based on local geology and water sources. When individuals migrate to new regions, their skeletal chemistry reflects their birthplace. By analyzing isotopes in teeth which formed during childhood and preserve their original isotopic composition, researchers can determine where individuals were born. Carbon isotope analysis reveals diet and subsistence patterns. Different foods, plants versus meat, marine versus terrestrial resources have distinctive carbon isotopic signatures. By analyzing carbon isotopes in bone, researchers can determine what ancient people ate. Applied to pyramid workers and monument builders, isotope analysis reveals who built these structures and how they lived. The analysis of pyramid workers' remains revealed that they received adequate nutrition and medical care, contradicting earlier assumptions about exploitation and harsh conditions. Astronomical software allows precise calculation of historical celestial positions. Modern computers can calculate where celestial bodies appeared in the sky at any date in the past or future. Researchers can determine exact alignments intended by ancient builders, revealing whether apparent alignments were deliberate or coincidental. This technology has confirmed intentional astronomical alignment at multiple sites. At Stonehenge, computer modeling confirmed that the monument's design precisely captures solstice alignments. At other sites, the analysis has revealed that some apparent alignments were actually accidental, the result of modern interpretation rather than ancient intention. This technology allows researchers to distinguish between deliberate astronomical engineering and coincidental alignment, providing more rigorous analysis than visual inspection alone. Experimental archaeology continues testing proposed construction methods. Recent experiments with ramp systems, lever configurations, and water lubrication techniques provide quantitative data about feasibility and labor requirements. Researchers have constructed replicas of ancient tools and attempted to move multi-ton stones using reconstructed methods. These experiments have validated some proposed techniques while suggesting that other theories strain credibility. Future experiments may test additional hypotheses about construction techniques. Researchers are planning experiments to test whether specific ramp configurations could have moved the largest Egyptian pyramid blocks. Others are investigating whether counterweight systems could have lifted massive stones. These experiments generate data that informs scholarly debates about construction methods. Genetic analysis reveals population movements and relationships. Ancient DNA extracted from burial sites illuminates migration patterns and genetic relationships between populations. DNA analysis has revealed that populations moved across vast distances, mixing genetically and culturally. This may reveal whether populations sharing architectural traditions were genetically related, suggesting knowledge transmission through family lines, or whether architectural similarities resulted from independent development or cultural contact. Genetic analysis has also revealed unexpected population movements and mixing. For example, analysis of ancient DNA from European sites revealed that populations migrated from the steppes into Europe, mixing with existing populations. These migrations coincided with cultural changes, suggesting that population movement facilitated knowledge and cultural transmission. Satellite imagery and ground-penetrating radar continue revealing subsurface features. Satellite imagery can reveal subtle variations in vegetation or soil color indicating buried structures. Ground-penetrating radar sends electromagnetic pulses into the ground and measures reflections, creating images of subsurface features. At Stonehenge, recent surveys using these technologies identified previously unknown structures in the surrounding landscape. Similar surveys at other sites may reveal previously unknown features. Beneath Stonehenge's visible monuments lies a complex landscape of buried structures, ditches, pits, and other features that are only now being systematically documented. These subsurface features provide context for understanding how the monument functioned within its larger landscape. The convergence of these technologies creates unprecedented opportunities for discovery. A site that was thoroughly excavated decades ago using conventional methods can now be re-examined using LiDAR satellite imagery and ground-penetrating radar, potentially revealing features missed by earlier investigations. Isotope analysis can provide biographical information about individuals whose skeletal remains were excavated decades ago. Astronomical software can precisely determine alignments that earlier researchers could only estimate visually. These technologies don't replace traditional excavation, but complement it, providing new perspectives on familiar sites. The pace of discovery is accelerating. Each year brings new technologies and new applications of existing technologies. Drone-based LiDAR surveys are becoming more affordable and accessible, allowing smaller research teams to conduct surveys that would have been impossible a decade ago. Genetic analysis costs are declining, making ancient DNA analysis feasible for more sites and more individuals. Computational power continues increasing, allowing more complex astronomical calculations and more sophisticated data analysis. These trends suggest that the coming decades will bring discoveries that fundamentally transform our understanding of ancient civilizations. Contemporary technology is generating new data about ancient structures, suggesting that our understanding remains incomplete and that significant discoveries likely await in coming decades. The monuments we've examined in this exploration represent only a fraction of what ancient peoples constructed. Many sites remain undiscovered, buried beneath earth or ocean. Many known sites have been only partially investigated. The technologies now available allow us to see beneath the surface, to analyze materials at molecular levels, to calculate ancient celestial positions with precision, and to trace population movements through genetic analysis. These capabilities promise to reveal new insights about how ancient monuments were built, who built them, and what they meant to the people who created them. The story of ancient megastructures is far from complete. Future generations of archaeologists, equipped with technologies we can barely imagine, will continue discovering new aspects of these remarkable structures and the civilizations that created them. The enduring mystery. We've explored contemporary research methods and recognized the promise of new discoveries in coming decades. Yet as we near the conclusion of our exploration, we must confront a fundamental truth. Some questions about ancient megastructures may never be fully answered. This final chapter invites us to reflect on the limits of archaeological knowledge and what those limits reveal about the nature of understanding itself. Some questions resist definitive answers despite centuries of investigation and modern technological advances. We may never know the precise motivations of individual builders, what thoughts occupied their minds as they quarried stones or positioned them with precision. We may never recover the complete technical procedures used in construction, the specific sequences of steps, the exact tools employed, the precise methods of coordination. We may never recover all lost knowledge or identify all undiscovered sites. Vast regions of Earth remain archaeologically unexplored. Underwater archaeology has barely begun investigating submerged landscapes. We may never fully understand the spiritual or philosophical frameworks that shape these structures, the cosmologies and belief systems that made monument building seem essential. These limitations reflect inherent challenges in studying the distant past. Archaeological knowledge depends on surviving evidence. Organic materials decay over centuries. Wood-bone leather and cloth materials that would reveal much about ancient life typically survive only under exceptional conditions. Written records are lost through fire, flood, and deliberate destruction. The Library of Alexandria's destruction eliminated countless texts. Spanish conquest of Mesoamerica resulted in burning of Maya and Aztec codices. Oral traditions fade when speakers die without transmitting knowledge to the next generation. We work with fragmentary remains, inferring larger patterns from incomplete data. A few pottery shards, some stone foundations, scattered bones. From these fragments we attempt to reconstruct entire civilizations. This necessarily limits certainty. We can establish probability. Certain explanations are more supported by evidence than others, but absolute proof often remains elusive. Consider what we've lost. If the Library of Alexandria had survived, we would possess detailed records of ancient knowledge. If Maya codices had been preserved, we would understand Mesoamerican astronomy and mathematics directly, rather than inferring them from monuments. If oral traditions had been recorded, we would possess detailed accounts of construction methods and purposes. The loss of these sources means we're working with incomplete information, trying to reconstruct sophisticated intellectual traditions from fragmentary remains. We're like archaeologists of the future, trying to understand modern civilization from a few scattered artifacts. Perhaps a computer circuit board, a photograph, a fragment of writing. From such limited evidence, could they accurately reconstruct our world? Yet this uncertainty itself offers value. The enduring mysteries maintain humility about our understanding. They invite continued investigation and fresh perspectives. Each generation of archaeologists reinterprets ancient monuments through contemporary frameworks, revealing new meanings. The monuments resist complete understanding, inviting continued study. They remind us that ancient peoples possessed depths we continue discovering, resisting easy categorization or complete comprehension. The monuments won't yield all their secrets. This incompleteness is not a failure, but an invitation to continued investigation, to humility about what we know, to respect for the complexity of the past. The monuments themselves persist, outlasting the civilizations that built them. They continue inspiring wonder and investigation. Each generation discovers new aspects, asks new questions, applies new technologies to old mysteries. This ongoing dialogue between present and past suggests that the monument's significance extends beyond historical understanding to something more fundamental, a connection across time to human creativity and aspiration. The monuments speak to us across millennia, inviting us to understand not just how they were built, but what they reveal about human nature and human possibility. Perhaps the ultimate lesson is that some mysteries should endure. The monument's power partly derives from their incompleteness, from questions that linger despite centuries of investigation. In our age of information, abundance where answers seem always available through internet searches and databases, the ancient structures remind us that profound mysteries can persist. They invite lifelong contemplation rather than quick answers. They suggest that some questions matter more than their answers, that the process of investigation, the wrestling with uncertainty, the attempt to understand something that resists complete understanding may be more valuable than definitive answers. Consider what would be lost if we solved all mysteries. If we knew exactly how Stonehenge was built, exactly what it meant, exactly how every detail functioned, would it remain as compelling part of Stonehenge's power derives from its incompleteness? We can observe the stones measure their positions, calculate their alignments. Yet the full meaning remains partially obscured. This obscurity invites imagination, contemplation, and continued investigation. The monument becomes a mirror in which each generation sees its own concerns and questions reflected. The same applies to all ancient megastructures. Their power derives partly from what we know and partly from what remains unknown. The knowledge we've gained, understanding construction methods, recognizing astronomical alignments, appreciating the sophistication of ancient peoples, deepens our respect for these structures. Yet the mysteries that remain, the purposes, we haven't fully grasped the knowledge systems, we haven't completely reconstructed the spiritual frameworks, we can only partially understand, maintain the monument's capacity to inspire wonder. The enduring mysteries of ancient megastructures represent not failures of knowledge, but reminders that human understanding has limits, and that some questions may be more valuable than their answers. The monuments stand as evidence of human ingenuity, ambition, and meaning-making. They demonstrate that humans across cultures and centuries have invested extraordinary effort in creating lasting structures that connect earthly existence to cosmic order. They reveal that spiritual and philosophical concerns transcend practical survival needs. They suggest that humans possess fundamental drives toward creating meaning, toward connecting to something larger than themselves, toward leaving legacies that outlast individual lives. Yet the monuments also humble us. They remind us that despite modern technology and scientific methodology, much about the past remains beyond our complete understanding. They suggest that the further we look into history, the more we recognize how much we don't know. This recognition itself is valuable. It maintains intellectual humility. It prevents us from assuming that our current understanding is complete or final. It invites continued investigation and openness to new perspectives. As we conclude this exploration of ancient megastructures, we return to where we began, standing before monuments that continue to perplex and inspire us. The stones remain silent witnesses to civilizations long vanished. They invite us to wonder, to investigate, to attempt understanding. They remind us that human history extends far deeper than written records, and that civilizations of considerable sophistication flourished long before the historical period we typically study. They suggest that human nature, the capacity for meaning-making, for cooperation toward shared purposes, for creating beauty and significance, has remained constant across millennia. And they remind us that some mysteries, some questions that resist definitive answers, may be precisely what we need to maintain wonder, humility, and the ongoing dialogue between past and present that gives history its meaning. Over the past 2.5 hours, we've journeyed across continents and centuries, examining some of humanity's most remarkable achievements. We've stood before Stonehenge's precisely aligned stones on the English plains, explored Göbekli Tepe's ancient temples, predating agriculture, confronted Baalbek's impossible foundation, stones marveled at Puma Punku's interlocking precision, witnessed Easter Island's Moai standing against environmental collapse, and considered the astronomical knowledge embedded in monuments across the globe. We've examined construction techniques, labor systems, and knowledge transmission. We've explored what researchers have discovered with confidence, what scholars continue debating, and what mysteries still resist definitive answers. What emerges from this exploration is a recognition of human capability that transcends particular technological eras. Ancient peoples possessed sophisticated knowledge of mathematics, astronomy, and engineering. They organized labor on remarkable scales. They invested enormous resources in projects expressing their deepest values and beliefs. They created monuments designed to endure for centuries, connecting earthly existence to cosmic order. Yet perhaps more importantly, we've recognized the limits of our understanding. Archaeological knowledge depends on fragmentary evidence. Organic materials decay. Written records are lost. Oral traditions fade. We work with incomplete information, inferring larger patterns from scattered remains. This necessarily limits certainty. We can establish probability, but absolute proof often remains elusive. Yet this uncertainty itself offers value. The enduring mysteries maintain humility about our understanding. They invite continued investigation and fresh perspectives. Each generation of researchers discovers new aspects, asks new questions, applies new technologies to old puzzles. The monuments continue inspiring wonder and investigation. This ongoing dialogue between present and past suggests that their significance extends beyond historical understanding to something more fundamental, a connection across time to human creativity, ambition, and meaning-making. Why does this matter? Because these monuments remind us that human nature, the capacity for meaning-making, for cooperation toward shared purposes for creating beauty and significance, has remained constant across millennia. The builders of Stonehenge and Göbekli Tepe Baalbek and Puma Punku Easter Island and countless other sites possessed intellectual and emotional depths similar to our own. They grappled with questions about meaning and purpose. They invested effort in projects transcending individual lifespans. They understood themselves as part of communities extending across time. Understanding their achievements reminds us that human capability, knowledge, and meaning-making transcend particular technological eras. Modern technology amplifies human capability, but it doesn't replace the fundamental capacities that allowed ancient peoples to accomplish extraordinary things. These monuments also offer perspective on contemporary challenges. Easter Island's environmental degradation reminds us that resource overexploitation produces consequences regardless of historical period. Ancient societies faced sustainability questions we continue facing. The knowledge transmission systems of ancient civilizations, oral tradition, apprenticeship, ritual practice offer insights into how knowledge persists across generations. The integration of practical and spiritual knowledge in ancient monuments suggests frameworks for addressing modern challenges requiring integrated thinking. The motivation of ancient builders, driven by spiritual significance, social cohesion, and participation in projects larger than themselves, reminds us that humans are motivated by meaning and purpose alongside material compensation. History is not static. New discoveries continue emerging. LiDAR technology reveals previously hidden structures. Isotope analysis illuminates ancient populations. Astronomical software calculates historical celestial positions with precision. Genetic analysis traces population movements. Each technological advance generates new data suggesting that our understanding remains incomplete and that significant discoveries likely await in coming decades. The monuments we've examined represent only a fraction of what ancient peoples constructed. Many sites remain undiscovered. Many known sites have been only partially investigated. Future generations of archaeologists will continue discovering new aspects of these remarkable structures and the civilizations that created them. We're drawn to history because it connects us to something larger than ourselves. The monuments stand as evidence that humans across cultures and centuries have invested extraordinary effort in creating lasting structures. They demonstrate that spiritual and philosophical concerns transcend practical survival needs. They suggest that humans possess fundamental drives toward creating meaning, toward connecting to something larger than themselves, toward leaving legacies that outlast individual lives. Studying the past enriches our understanding of what humans are capable of, what we value, and what endures. The ancient builders speak to us across millennia, inviting us to understand not just how they accomplished their remarkable feats, but what those accomplishments reveal about human nature and human possibility. Thank you for joining this journey through ancient mysteries and human achievement, for spending these hours exploring monuments that continue to inspire wonder and investigation, for engaging thoughtfully with evidence and ideas, with certainties and uncertainties, with what we know and what remains unknown. If you found this worthwhile, there are more stories waiting other explorations of human achievement, mystery, and meaning. But for now, rest well. May these ancient monuments and the people who created them accompany you into sleep, reminding you that human creativity, ambition, and meaning-making have endured across millennia and will continue into the future. Good night.